So today I will be talking about equilibrium and their stabilities and their stability for two-dimensional flows. So we consider two-dimensional flows. And for them we consider equilibrium and their stability. So two-dimensional flow, x dot equals to f of xy, y dot equals to g of xy. Again, so x and y describe variables describing state of our dynamical system. F and g smooth enough, they have at least continuous first derivative. And so when we want to introduce equilibrium, we already know this concept. Equilibrium is such pair of numbers or point on the plane xy such that x equals x of t equals to x capital and y of t equals to y capital for any t is a solution for a system. So it makes our system identity. And about stability now. Stability. So there are two definitions of stability. First is asymptotic stability. So asymptotic stability, it requires convergence of solutions to equilibrium. So there is delta such that if x naught minus x capital squared plus y naught minus y capital squared less than, say, delta squared, then x of t tends to x capital, y as a function of t tends to y capital when time tends to infinity. So here x naught is value of x, so it's initial value of x, and y naught is initial value of y. So this is initial conditions. And Lyapunov stability, there is another definition of stability, which is called Lyapunov stability or neutral stability. So this stability doesn't require convergence, but it rules out divergence. So for any epsilon, there is delta such that if x naught minus x capital so y naught minus y capital less than delta squared, from here it follows that x of t minus x capital squared plus y of t minus y capital squared less than, say, epsilon squared for any t. So it's always will be in neighborhood of, if we started in the neighborhood of the equilibrium, then our solution will stay in the neighborhood of this equilibrium. So our analysis of stability of equilibrium, we will start by considering linear flow. So let's consider linear two-dimensional flow. So this will be linear and homogeneous. X dot equals to a11x plus a12y and y dot equals to a21x plus a22y. And so what we will do, we'll introduce vector U with components X and Y. We introduce matrix A with entries A11, A12, A21, A22, and therefore our system can be represented like this. U dot equals to A times U. So U is vector here, A is matrix. What we can say about linear system: if matrix A is non-singular, if, so I can put it like this, if determinant of A is not zero, then 0, 0 is the only solution if is, let's say, is the only equilibrium. And therefore, what we do, in fact, we analyze stability of 0, 0. How stability of this equilibrium depends on entries of matrix A. So this is our problem. Well, I can state straight away that if the solution of, so if B1, lambda 1, and vector B2 and number lambda 2 is eigensolution for matrix A, then our solutions will be given like this. U of t is C1 B1 e to the power of lambda 1 t plus C2 B2 e to the power of lambda 2 t, where C1 and C2 are constants found from initial conditions. So let us prove this statement. Let's make substitution. U equals to some matrix B times some V, where matrix B has columns B1, vector B1, and vector B2, which are eigenvectors of matrix A. Therefore, U dot equals to A U will be represented as B times vector V equal to A B times vector V, so V dot here. So derivative. So sorry. So if U equals to BV, then from here U dot is also equal to BV dot, because matrix V is constant. So we got this. And here we want to analyze what is this product of matrices A and B. AB is A times B1, B2. This is matrix with first column A times vector B1 and second A times vector B2. So since B1 and B2 are eigenvectors, then A times B1 is lambda 1 times B1, and A times B2 is lambda 2 times B2. And this can be represented as product of this lambda 1, 0, 0, lambda 2, and so sorry. So it is, this one is correct, but we will have B1, B2 in front of this matrix. So you can see this matrix times this matrix. It will be B1 times lambda 1 in the first column, and second column will be B1 times 0 plus B2 times lambda 2 will be B2 times lambda 2. So this is, in fact, matrix B times this diagonal matrix D, where D is lambda 1, 0, 0, lambda 2. Thus, what we got, AB equals to BD, and therefore PV dot, now we're getting back to this, and I will again, BV dot equal to ABV is now it equals to B times dV. And if B is non-singular, B can be cancelled by, so we multiply by inverse of B from the left. So therefore we got V dot equals to lambda 1, 0, 0, lambda 2 times V. And from here we can see, so if V has components V1, V2, then we'll have V1 dot V2 dot equal to lambda 1, 0, 0, lambda 2, V1, V2. And from here we get V1 dot equals to lambda 1, V1, V2 dot equals to lambda 2, V2. From here we get V1 is V initial value of V1 times e to the power of lambda 1t, and V2 of t equals to initial value of V2 e to the power of lambda 2t. So this and this we can replace by C1 e to the power of lambda 1t, C2 e to the power of lambda 2t. And now getting back to our original vector u, which is xy, and which is b times v1, v2. So this will be equal to b1. So matrix B is b1, b2 times v1 and v2 we now know c1 e to the power of lambda 1t, c2 e to the power of lambda 2t. Therefore, we got c1 b1 e to the power of lambda 1t plus c2 b2 e to the power of lambda 2t. So this is what we got. X, y equals to this. So our statement is proved. So based on this result, we can make statements about stability of equilibrium 0, 0. So what we see, if lambda 1 and lambda 2 are both negative, then x tends to 0 and y tends to 0. And therefore, what we can say is the statement. Let's solve it. For now, we consider the case when lambda 1, lambda 2 real numbers. So if they're real, then everything is straightforward. Case 1, lambda 1 negative, lambda 2 negative, then 0, 0 is stable, and it's called, it has a name, it's called stable node. 0, 0 is stable node. Or there is another word for this thing. Case 2. One of lambdas negative, another lambda positive. So then 0, 0 is unstable because we don't have divergence to 0 of x and y because of this term. This term will first term tends to 0. This would tend to 0, but this wouldn't tend to 0. This would tend to infinity. And therefore, 0, 0 is unstable, and in this case, it is called saddle. You already know this term, saddle. Case 3, both lambdas positive. Then 0, 0 is called unstable node, and it's also called source. So among these cases, there is difficult subcase when lambda 1 equals to lambda 2. So what we know if lambda 1 equals to lambda 2, then there are two options. One option is when B1 and B2 are linearly independent. If B1 and B2 are linearly independent, then we have a case which is called star. B1 and B2 are linearly independent. Then we have star. Then 0, 0 is called star. It's called star because there is convergence in all directions. There is convergence with the same, so trajectories look like straight lines, depending on initial conditions. So what would be good to say if, for example, lambda 1 is not equal to lambda 2, then it is not star because, for example, we start here and this, for example, B1 direction, this is B2 direction, and if we start here, usually they bend our solutions because they get closer to one of Eichen directions faster than to another. So it could be something like this. So in this case, lambda 2 is more than lambda 1, and say and if they converge, then they are less than 0. So this is to compare with star. Second case, if B1 and B2 are parallel, then in fact we need to, so we still can do all our transformations, but so solutions will be looking slightly different because matrix B is singular in this case. But what happens in reality, solution will look like this. It will have some ending. So this kind of solutions, if it's, and from here they get like this also. So this is called degenerative source. Okay, and now another difficult case when lambda 1 and lambda 2 are complex conjugates. So alpha plus minus alpha. And Then B1, B2 also will be complex. It will be real, let's say minus plus I be imaginary. So this is complex case. So in this case, our solutions will look different. So we can use, again, we still have U equal to C1, B1 e to the power of lambda 1t plus C2, B2 e to the power of lambda 2t, but we can use Euler formula e to the power of lambda t, say lambda 1t. It would be e to the power of alpha times cosine beta t minus I sine beta t, so Euler's formula. And then generally this can be at the end reduced to this. So in compact way, it can be represented like this, equals to e to the power of alpha t. So our matrix B, so B real, imaginary part, and here will be cosine beta t sine beta t minus sine beta t cosine beta t. So you don't need to remember maybe this formula, and here will be C1, C2. So this is, it will be at least real part of solution when eigensolution is complex, can be represented like this. And here we have extra cases. So there were, let's say, 3 cases before. Case 4, when alpha is negative. So then 0, 0 is stable, and it's called stable spiral or stable focus. And case 5, alpha positive. So then 0, 0 is unstable. Spiral or focus. And then case 6, when alpha equals to 0, in this case 0, 0 is Lyapunov stable eventually, so it's not asymptotically stable, it's not unstable either, and it's called center. So, and this pretty much completes classification of equilibria in two-dimensional flows. So all these considered cases can be associated with trace and determinant of matrix A. So to do this, let's get back to lambdas. Lambdas are roots of this equation A11. So they are eigenvalues of matrix A, and they are found like this. This determinant is 0, and this brings to characteristic equation. So this will be lambda squared minus A11 plus A12 lambda plus A11 A22 minus A21 A12 equals to 0. So this is trace of matrix A, and this is determinant of matrix A. And therefore, we can put it like this, lambda squared minus trace A times lambda plus determinant A is 0. and lambda 1, 2. So according to formula for roots of quadratic equation, it will be trace A plus minus square root of trace A squared minus 4 determinant A divided by 2. And now what we can from looking at this, we can decide at what conditions for trace and determinant should be satisfied for different cases of which were considered before, for different classes of equilibrium 0, 0. So for example, if trace A is negative and this square root less by absolute value, less than absolute value of trace A, then lambda 1 negative and lambda 2 negative. It's, yeah, because this is negative number and this, even we add it's by absolute value less than this negative number. So again, this is negative number, and when we subtract something, it is fine, it is still negative. When we add something which is by absolute value less than trace A, then it will be negative. And so this is, so in this case, we will have both lambdas are negative. And what it means? It means now when this is less than trace of A, this is less than trace of A means determinant of A is positive. So if determinant of A is positive, and from trace squared A subtract something, and therefore what we then when we take square root, it will be small by absolute value than trace A. Therefore, what we can, another observation is when lambda 1 and lambda 2 are real. So lambda 1, 2 real if trace squared A minus 4 determinant A is positive. And this, we can put it like, let's say this is trace A, this is determinant A. So this is positive under this curve, it's quadratic curve. This. So in this area we have imaginary. And real, so lambdas and real lambdas is everywhere else. And then what we found that if determinant A is positive and trace is negative, it will be stable. Therefore, here we conclude this here should be stable focus. And stable here should be here, then here will be stable node. And similarly, here then it should be unstable focus, and here unstable node. We can check it. And if determinant is negative, then it will be subtle. And it's easy to see from this formula. If determinant is negative, then trace squared minus negative number, this will be more larger than trace A squared. And therefore, when we add and subtract this square root to trace A, we will have two numbers different by sign. Therefore, here will be subtle. Well, and last comment, if trace A is 0 and determinant A positive, we have center. So it will be exactly in the middle between stable focus and unstable focus. Okay.